Okay, so today we're going to try to wrap up chapter 1 on sets. We're going to talk about ways to build new sets, given two sets. There's some special operations that you can do to combine sets. So in 1.5 specifically, we'll talk about taking the union, the intersection, and the difference of two sets. Okay. So suppose you have two sets. So given sets A and B, we can define three new sets. First one, the union of A and B. Okay. The notation for the union is A and a U and a B, but there's no line on the right side of the U, and that's just like A. So when you see this, most people don't say the union of A sets A and B. I mean, you just say A union B. Okay, A union B. The union of sets A and B is the set of all objects in A or in B. Of all objects that are in A or in B. So the union, it's like coming together. You take all the stuff that's in A, all the stuff that's in B, put it in a big, empty those two boxes into a big box. We'll call that the union. So using set builder notation, A union B is the set of all elements X such that X is an element of A or X is an element of B. Okay, remember that sets are repetition free, so if something's in both sets, you don't have to rewrite it twice. Just throw it in once, and it's already in the set. Okay, so the second set is the intersection of A and B. And the symbol for intersection is an upside down U. So A intersect B. Okay, so that's how I would read that. If I see that, I would read it as A intersect B, or the intersection of A and B. Okay. So you think about when you're driving a car, you pass an intersection. An intersection is where two roads overlap. Really, if you think about it, you're driving on one road, an intersection is where another road overlaps it. So the intersection is where the two roads overlap. Think of it as where these two sets overlap. What are the things that are in both sets at the same time? Okay, so the intersection of A and B is the set of all objects in both A and B. So A intersect B, using set builder notation for our definition, would be the set of all objects X such that X is in A and X is in B. Any questions so far? Example. A is a set containing the numbers 1, 2, 3, and 4. B is a set containing the numbers 3, 4, 5, and 6. C is the set containing the numbers 5, 6, and 7. A union B. So you take all the elements of A, add anything else that's already not that you've not already included from B. So it'll be 1, 2, 3, 4. I've already got 3. I've already got 4. So I need to add 5 and 6. There's the A union B. Any questions about that? The intersection, so you actually have, what elements are in both sets? 3 and 4. So A intersect B would be the set containing 3 and 4.
And then neither sets have anything in common. It's the empty set.
So for example, if A and C have nothing in common, so if A intersects C, there's no elements in common. So you just write it as the empty set containing nothing. And in this case, if two sets, the intersection of two sets is empty, we say that these two sets are disjoint. We say A and C are disjoint. Okay. If there's nothing in the intersection, there's no overlap within these two sets, so they're disjoint sets. Okay. So if the intersection of two sets is empty, we say they're disjoint. All right. Before going to the, we're talking about. I told you we're going to talk about the union, intersection, and difference. Before going on, I want to bring up a topic from chapter 7 called Venn diagrams. You may have seen these in probably in high school or middle school or something. I mean, but just to help us visualize these sets, I'm going to draw some Venn diagrams for these sets. So here's set A. Venn diagrams you use circles to represent sets. And it just helps us visualize these relationships. So A union B, I'm going to shade in A union B. So everything that's inside A or inside B, this whole region, that's A union B. So this is a Venn diagram for A union B. Okay? So let's draw a Venn diagram for A intersect B. A intersect B. So you have two sets again, and it may be that the intersection has nothing in it, but usually, to make a general Venn diagram, you have your sets possibly overlapping.
Would A union B include the overlap?
Yes. Like for example. Here in this example, 3 and 4 were in the intersection, and 3 and 4 are also in the union. Okay, so it includes everything that's in A or in B. It could potentially be both. So mathematically, when we say the word "or," we don't mean either or. It just means the mathematical definition of "or" is it's one or the other or both. Okay. So this is A union B, this would be A intersect B, where the two sets overlap. Okay. I mean, all of section 1.7 is on Venn diagram. We'll talk more about this a little bit later today. How do you draw a Venn diagram for more, for two sets, would be instructive, but when we start getting more complicated, 3 sets, it can be kind of useful to visualize. Any questions? Any other questions? Okay. Let's talk about the difference now. The difference read it that way, A minus B. Okay? So it's just like, you use the word take away for like subtraction. You start with the set A, you take away anything that's in B. Okay? So is the set, the difference of A and B is the set of all objects that are in A but not in B. And so if you start out with a set A and just take out anything that's also in B, then you have A minus B.
So, is it the same as A minus A intersect B?
Mm-hmm. You can think of it that way. So it's set of all x such that x is in A and x is not in B. So this is A, this is B. Talking about this kind of moon-shaped piece here. This is the part of A. These are all the elements that are in A but not in B. Yes.
So A difference B is different than B difference A?
Yes, it is. That would be, you start with the set B, take out anything that's in A. Yeah, so the first one, the elements are in this set, not in this set. Okay? So this would be the Venn diagram for that. And so your question was, so look at this. If you took all of A and you subtract off the picture for A intersect B, what do you get? You get this, right? So here's this piece right here is A intersect B. He said, is this the same as A take away, what did you say?
A minus that A intersect B.
Yeah, A minus A intersect B.
All of the others go both ways, though, right?
Sorry?
A intersect B is the same as B intersect A.
Correct. Yeah, if you have just one, a union, or you have two sets with a union or an intersection, the order is commutative. I mean, you don't have to worry about the order. So right. If you think about it, an and statement, you think of, and if the point is in A and in B, that's the same the point is in an object is in B and in A. Now, if you have, we'll talk about this. I'll probably get to section 1.7. If you have three sets, and your one's a union, one's an intersection, then you're gonna have some set of parentheses to just make it absolutely clear what set you're talking about. Okay. Any other questions? These are good questions. Okay, so let's do. The same example, still over here. What if I had, so in the previous example, what would A minus B? Remember, A is a set with 1, 2, 3, and 4. B is a set 3, 4, 5, 6. So A minus B would be 1 and 2. Have 1 and 2 in it. Okay, so for the same example, what if we did B minus A? So this would be any element that's in B and not in A. Well, B was a set 3, 4, 5, 6. So I have to get rid of the 3 and the 4. I'm left with just the numbers, the elements 5 and 6.
Say you did A minus C. Since there are no elements in C that are in A, would it just be set A?
Yep, it would A minus C. Well, it would just be A because It's the easiest way to write it, because what elements of A are in A but not in C? All of them. So the whole set A is in A minus C. That's kind of what he was pointing out. If you're really taking away the intersection, as he says, well, the intersection is empty, you're not taking away anything. Any other questions?
What happens if the first one's the empty set, or do you run into that?
Well, I mean, you could do an example like that. So okay, so take the empty set and take away anything that's in A. You're still going to have that. I mean, the empty set, if you start with the empty set, you're gonna end up with the empty set, and you subtract anything else.
And A minus the empty set would just be A.
Mm-hmm. A minus the empty set would be A. That's the same, kind of equivalent to that. Right. Okay. Any questions? All right. How about a few more sets? We defined intervals earlier in chapter 1. This is probably where, if you've seen unions, if you've had calculus, you've likely seen unions, or maybe pre-calculus. You've seen unions because oftentimes we talk about a domain of a function. Oftentimes there's a chunk of the real line, or even just one number you have to eliminate from the domain of a function. So oftentimes we use the union symbol to say the domain is, say, all our numbers less than 2 and all our numbers greater than 2, for example. Okay, so let's do some examples with some intervals. So this is an interval, okay? So it's the interval from 2 to 5. Since I have closed brackets, this means the set of all numbers between 2 and 5, including the endpoints 2 and 5. So the interval from 3 to 6 is all the numbers between 3 and 6, including 3 and 6. Okay, so these are kind of, might be helpful to draw these sets. Probably used to seeing these on the real line. So the set interval from 2 to 5, we go from 2 to 5, and if I shade in the real line here, if I had a different color, I would use it. But the union, this set goes from 3 up to 6.
So we could rewrite it as 2 to 6.
Yeah, since everything, the easiest way to rewrite this would be, it's actually one interval. It's equivalent to one interval. It starts at 2, and every real number up to 6, and including 6, is shaded in. So this set is equal to the interval from 2 to 6. What if I change that to an intersection symbol? Now you're looking for, where do these two intervals overlap?
3 to 5.
Yeah, so where did I draw them twice? So from 3, it's still, well, from 3 to 5, do I still include the endpoints? Yeah, because 3 is in both sets, and 5 is also in both sets, so I would include the endpoints. What if I did an interval from 2 to 5 minus an interval from 3 to 6? So start with 2 to 5, and then take out any number that's also in this interval. Bracket 2. What's the right endpoint? What number? 3. That's parentheses. Because if the number 3 is in this set, I've got to take it out. So I don't want to include it anymore in this set difference. So it goes. Imagine you start with this picture and you just erase everything that's in the interval from 3 to 4. What's left? Well, I erased everything, and then I actually erased the number 3, so it's kind of like an open interval now. Okay. Any questions? you've probably seen, like I said, the connection, you've seen functions like, so that equals 1 over x minus 2, for example. The domain, you've seen this, the domain is a set of all x coordinates that you're allowed to plug in the function. That's one way to think of it. But, we'll talk about functions this semester as just sets of points in the real plane. So if you look at the graph of this, function, it's going to look like, well, there's going to be a problem at the number 2. It's going to have what we call a vertical asymptote at x equals 2. So the mathematical definition of a function, you think of it as just a set of points. A specific set of points where no 2 points have the same x coordinate. So the domain would be all the first coordinates of all the points. Well, this line keeps going forever to the left and goes all the way up to the number 2. So the domain would be from negative infinity to 2, parentheses. But then also on this set, these points start right after 2 and go all the way to the right to infinity. So this is how you've probably seen the union symbol before. The union of 2 intervals. It might be a domain problem or a solution to an inequality or something. So most of the time, you can get through calculus, I guess maybe just seeing the union symbol. Okay. Any questions about that? Another example. A is a set containing 0 and 1. B is a set containing 1 and 2. What is, first part, what is A cross B intersect B cross B? Maybe we should do this in parts and steps. So let's think about A cross B. So this is how many order pairs are going to be in A cross B? 4, right? 2 times 2. So it's going to be, so A cross B is going to be the set containing points, order pairs where the first coordinate is an A and the second coordinate is B. So it's 0, 1, 0, 2, 1, 1, 1, 2. So there's A cross B. Now when I take the intersection of that set with P cross B, so these are order pairs where the first and second coordinates come from B. So how many elements are going to be in B cross B? 4 as well. So 2 times 2. So it's going to look like 1, 1, 1, 2, 2, 1, and 2, 2. Okay. So now that I have all these cross products written out, what's the intersection of these two sets? Which order pairs are in both sets? 1, 1, 1, and 1, 2. Okay. That's the answer.
Is there a shortcut to figuring that out, or you have to do it long?
I mean, you just think about it. I mean, you can think about. I mean, you kind of go one at a time. Well, 0 is not in B. So for stuff B cross B, the coordinates are either 1s or 2s. So you think about how can I make a point in A cross B that only has 1s and 2s? I mean, so that's where you can think of it. So you can just generate without. Well, the first the first coordinates have to come from A, and the second coordinates have to come from B, and they only have, you can only use, 1 to 2. I mean, by the time you start thinking about it, it's just mine, just write them all out.
If they were in parentheses, would you just do that from left to right, or is one more important?
Okay, so if these parentheses were missing right here,
Yeah.
then you couldn't do it. No, you'd have to have the parentheses to be correct. Because if I didn't have this, yeah, you're right. So which one would have precedence? You would have to go like from left to right. So it would be like A cross B union B. So well, I guess let's see. If I wrote this A cross B union B cross B, would this be ordered triples, where the first element is in A, the second element is in B intersect B, which is just B, and see what I'm saying? It just wouldn't. It would be ambiguous. So it just would be, it shouldn't be done. I mean, you should, to be precise. It would look like this might be a set of ordered triples, but again, B intersect B is just B. The elements that are in B and in B are just B. So this would look like A cross B cross B. Well, in the previous section, they wanted you to think of this as ordered triples. So, but it would look confusing when you have B cross B. So, I guess they could make that an example, but this doesn't happen. Usually, when you have, when I've seen cross products with more than 2 sets, it's like just R cross R cross R. That's really what you're going to deal with in like Calc 3 class. You'd see R the third. Any of these other ones where they have multiple cross products, in this book, it's more informative. It's trying to get you to think about the definitions. Okay.
If we had something like that, A cross B intersect, and then it was, instead of B cross B, it was B cross C, would the answer just be B? Since B is the only thing that both of them have in common?
Well, no, because anytime you have A cross B, now you have ordered pairs. Okay, but B doesn't have any ordered pairs in it. Any other questions about this example? Instead of moving to the board, I'm just going to erase this and do another example. So, does everybody have this? The thing is, you can go on video and pause it if you need to write something down. Alright, so let's make this a part B. What is A intersect B cross A? What is A intersect B? Just the set containing the number 1. That's what you meant, right, when you said 1? The set containing the number 1? Okay, and then you take that, the cross product of that set and A. This is going to look like ordered pairs where the first element is 1, the second element is, the second coordinate is an element of A. So this would look like 1, 0, 1, 1. First coordinates have to be 1. The second coordinates can be any number in any element of A. Well, there's only 2 elements of A, 0 and 1. Okay. Any questions? How about the power set of A minus the power set of B? The difference between the power set of A and the power set of B. So what's the definition of the power set of A? The set of all subsets of A, right? The set of all subsets of A. So let's just write this out. So the power set of A is a set, contains all the subsets of A. Well, it's got to have the empty set in it. That's a subset of every set. It's going to have 2 subsets where there's only 1 element. Okay, the set containing 0, the set containing 1, and then it's got A. or you could write it out, the set containing 0 and 1. Okay, that's the power set of A. Difference, then now the power set of B. So the power set of B contains all the subsets of B, including the empty set, the set containing 1, set containing 2, and B. Okay. Questions so far? So start with the power set of A, take out any set that's in the power set of B, take out any elements of the power set of B, and what are you left with? Yeah, the set containing 0, because you have to take out the empty set. Take out the set containing 1, that's in both in here, and then A. Okay. Any questions? All right. For section 1.5, right? So I'll keep updating your homework. Now, you guys have been doing really great, so I've decided to give you guys Monday off. So I'm not gonna collect any homework on Monday. Okay. So that was a joke. No, school's canceled. I mean, there's no class on Monday. So I'm not gonna make you guys turn your homework on Monday if you don't have class. So the homework's gonna be due Wednesday of next week. And
Is that the 22nd?
Yes.
page 18, number 2, and number 4, but only parts A, D, and G. Okay, and again, I posted this on Blackboard. Okay. All right, so that's a good break point. So. Okay, so let's continue with section 1.6. Talk about the complement of a set. Like, you're a very beautiful set. Yeah. Had to get laughing at my jokes. I'm trying to get some brownie points early in the semester. All right, so let's talk about the universe. When we talk about sets, the universe is kind of usually implied when you're talking about sets. It's the set of all the things you're considering at the time. Okay? So when we talk about like intervals, for example, intervals usually we think of as subsets of the real line, the real numbers. So, for example, if you're talking about an interval, the universe is usually implied to be the real numbers. Okay? So the universe, usually denoted by a capital U, think of it as the set of all objects under consideration. Okay? And it's usually, depending on your class, it's understood what your set you're talking about. You know, like in a calculus class, you're talking about real numbers or the real plane.
So real numbers would be a subset of universal set.
Yeah, well, sometimes I'm saying the real numbers can be a universal set for a specific set you're talking about. Because when I'm trying to talk about the complement of a set is everything else that's not in that set. So when I say everything else that's not in that set, do I mean all the people in Outer Mongolia? Do those people count? Because they're not in that set. I mean, no. So you got to define the universe as what are the things we're even considering? We're just considering real numbers. So if we have an interval, the complement of the interval would be all the real numbers that are not in that interval. Okay, so it's kind of like the inside and outside of a set. But you don't want to talk about everything in the universe of man. So we're talking about a universal set just for a particular set. Okay, so for example, like I said, if you have an interval, so for the interval from 2 to 5, for example, the universe is all real numbers. Okay. If you take a class like complex numbers or complex variables, you're talking about complex numbers. Well, real numbers are a subset of the complex numbers. So you can think of, when you're talking about in a complex numbers class, your universe is always the complex numbers or the complex plane. I mean, so just usually from context, when somebody's saying, okay, so take everything outside this set, you know what they're talking about then, because you're just confined to this universe. All right, so now we can talk about, or maybe another example I can book is prime numbers. When you say a number's not prime, am I talking about like square root of 2? No, I'm talking about, it's just implied, I'm talking about probably the natural numbers. Okay, usually when you look at prime numbers, you're only concerned with the natural numbers. So you look at prime numbers and composite numbers. Okay. So the natural numbers would be the example of the universe. All right. So now we can find the complement of set A. And here's the notation. It's an A with a bar on top. So you can call it like the complement of A. Some books will put like a C, like an exponent with a C for complement. But this is pretty standard. The complement of A. Okay. People might call it A bar, but so the complement of set A is the set of all objects in your universe. So all objects in U that are not in A. Okay. So the complement of A is all the elements in the universe take away A. One way you can define it. Instead of all points in the universe that are not in A. So for a Venn diagram, you have your universal set of things you're looking at. A is a set inside. So where would all the elements that are in the universe but not in A, what would that look like?
Shading everything around it.
Shading everything around A. Okay. That'd be the Venn diagram for A complement. Any questions so far? Give some examples. So the universe, usually when you talk about the rational numbers, remember the symbol is bold Q. What do you think the universal set would be if you're talking about the rational numbers? Some bigger set that contains the rationals. Real numbers. For the universe for the rationals is usually the real numbers. So think about this. What then would be the complement of the rational numbers?
Irrational.
The irrationals. I mean, so any number, any real number can either be written as a fraction of integers or cannot be written as a fraction of integers. And so that partitions all real numbers. So if you think of it as the real numbers take away the rationals, we call that the irrationals. Instead of all irrational numbers. So, we don't usually talk about irrationals as sets. I mean, I don't hardly ever need a symbol for the irrationals. But this is one way you could write it. You can write complement of the rationals. That's assuming that everybody knows you're talking about the all real numbers. Okay. Okay. There's another. Now I'm going to define a universal set. The universal set is going to have all the integers between 0 and 10. Okay, these are the only numbers I'm considering for this example. This is the universe. Okay. A is the set 1, 3, 4, 6, 7, 9. B is a set containing 1, 3, 5, and 7. What's the complement of A?
2, 5, 8, and 10.
Yeah, so you got it. Did you guys say 0? Almost all the even. I mean, there's 4 and 6, but so anything that's in the universe that's not an A. So 0, 2, what else? 5, 8, 10. Right here. What's the complement of B? Yeah, anything other than 1, 3, 5, and 7. So 0, 2, 4, 6, 8, 9, 10. Okay. Any questions? is the complement of A union B? So since the line is above the whole thing, you have to start with the set A union B, and then take the complement of that set. Okay. So so you got to think about what is A union B.
Everything in A plus everything in B.
Yeah, so what's not in A union B? And that's what the answer then. So anything that's not in A union B is 0. Anything else? 2, 8, 10. You guys agree? I like it? Okay. Believe it? You know, anything in the universe that you don't see in A and B. How about, let's see, what if, hold on a second. What if I did, is that the same as this? What if I split it up and did the complement of A union the complement of B? You get the same thing? Yeah. Well, we've got complement of A and complement of B already on the board. So now just take the union of these two sets.
0, 2, 4, 5, 6,
0,
9, 10,
2,
4,
4,
6,
5, 6,
8,
8, 9, 10. So, there's a little note you might want to make. So the complement of a union is not the same as the union of complements. Interesting. How about how about this set? The complement, how would you even read that? The complement of the intersection of A complement and B. Or something, yeah. The complement of A complement intersect B. So you've already you still have A complement on your paper. I just erased it. What's the intersection of A complement and B? So things that are not in A and also in B. So that'd be 5. Is that right? 5 is the only number that's not in A, but it's also in B. So the complement of that set would be everything except 5.
0, 1, 2, 3, 4.
Yeah. So there, that's faster. The universe minus set 5. I mean, you can write it out. It's set containing 0, 1, 2, 3, 4, 6, 7, 8, 9, 10.
That contain kind of all x and u, that's the x not equal to 5.
Yeah. Those are equivalent. But I guess the direction, sometimes the direction is they'll say, write it out, like write all the elements out and put them in braces or something. All right, any questions about complements? Okay, that about wraps up that. So a couple problems I want you to work on 1.6, and we'll go on to 1.7 next. 1.6, page 20, number 2, and number 6. Again, that's going to be due next at 20. So just gonna wrap up chapter 1 for now. I think we may come back to 1.8. We might not. But I think we got plenty of topics. We've covered plenty of topics in chapter 1. We can move on to chapter 2. After this. So, Venn diagrams. I'm just going to show you some more examples, specifically sets with unions and intersections with more than 2 sets. Okay. So when you have 3 sets, you have to draw your Venn diagrams. In the most general setting, all 3 would set to be intersecting like this, overlapping. Just label like this. Okay, so sets A, B, and C. Okay, so we're going to use this. This is kind of our starting point for our sets. So A union B union C. By definition, this is the set of all elements in A or in B or in C.
So it would be all 3 circles shaded.
Yeah, you shade in everything inside A, B, and C. What about if I change these to intersect? A intersect B intersect C. Let me draw another. So A intersect B intersect C would be the set of all elements in A and in B and in C.
So it would be that small little section.
So it's like this little triangular type region right there. A set that's where all 3 overlap. How about parentheses, A union B intersect C. So how could you describe this in words? It's the set of elements in A or in B and in C. So here's the trick. If you have, so really think of this as the union of, or sorry, the intersection of 2 sets. I'm going to draw the first set, I'm going to shade in the first set with like vertical lines. I'm going to shade the second set with horizontal lines, and then we'll look at where those 2 graphs overlap. Okay? So what does A union B look like? Yeah, all of A and all of B. So I'm going to use vertical lines for A union B. And then take this set, intersect it with C. So where does this set intersect C? So there's here where my horizontal lines are. So those 2 pieces, those actually three little tiny regions make up this set. So I'm going to erase now. I know where this is.
So that would be the same as A intersects C plus B intersects C minus A intersect B intersect C.
What is this plus talk about? I don't have A plus B. I mean union?
Yeah.
Yeah, so all these sets, you can come up with very complicated ways or very simple ways or but try to if you're asked to write this as a using unions and intersections, you try to find the easiest way to write it. So this is A union B, all the elements that are in A or B, and at the same time in C. Okay? All right. How about A union B intersects C? So what's the difference in these two expressions? I've just moved the parentheses. Let's see if it makes a difference. So I can do it here. All right. So now I'm going to start with B intersects C. All right. So B intersects C. Those are the points that are in the elements in B and in C. Oh, I burned the label. How about that? B intersects C is this football-shaped wedge right here. All right, this is B intersects C. Right? Okay. Now union A. So any element in this set is in A or it's in this set. So what do I need to add? All of that. Yeah. So add. Okay. So anything that got shaded at least once is in this set. Okay. So let's play. It's like a an animal on one ear. Tragic farming accident. Okay. So, that's how you see it, I guess. It's like staring at clouds. Okay, so is that the same as the previous example? So, from this example, it appears that it's really important where you place the parentheses, right? 'Cause that seems like it changes the set. So if I just wrote A union B intersects C, which one is it? Is it this one or is it this one? Does this mean A union B and then take the intersection of C, so like this? Or does this mean, well, I should take B intersects C and then union A, so I'd end up with this? The point is, you can't do this. If you have an expression with unions and intersections, you have to have a set of parentheses to be precise about what set you're talking about. Okay, so that's kind of what this picture is kind of leading us to believe. So for expressions with union and intersection, you must include parentheses. If it was all unions or all intersections only, just one or all unions, then you wouldn't need parentheses. If it's all intersections, then you don't need parentheses. But when you start mixing and matching unions and intersections, it makes a difference where you put the parentheses, so you can't leave them off. Okay, here's another example. let's work from the parentheses, inside the parentheses. So A union B, all right, I'm going to shade in everything in A and B. In A or in B. So, and we use vertical lines, there's A union B. What does A union C look like? Well, I'm going to shade in everything that's in A or in C. So horizontal lines. If I take the intersection of these two sets, I'm talking about which regions? What does the shading look like for the answer? Any region where they're shaded both times, right? Vertical lines was A union B, horizontal lines was A union C. So which regions got shaded in twice? It's like this one did. Okay. This one did. Well, actually, all of A did too, didn't it? Right? Yeah. So all of A. All of A. Anything else get shaded in twice? This little ear here. Interesting. I wonder if it's true that A union B intersect A union C is equivalent to A union B intersect C. So does this equal this? Proof by picture. Yeah, it is. It looks like a distributed property, right? Like I'm distributing a union over these two sets, and so it's exactly that. So we'll actually, this kind of leads us to believe this true statement that set does equal this set. They are equal, and when we get to we'll start talking about writing proofs. How do you show that two sets are equivalent? You remember how we said what the definition of how do you tell if two sets are equal? Two sets are equal. I mean, like if two sets are not equal because they don't have the same elements, right? The two sets are equal if they have exactly the same elements. So that's when we think about how we're going to prove that two sets are equal. We'll take an arbitrary element of this set and show that it also is in this set. Take an arbitrary element of this set and show that it's also in that set. I mean, so let's get this down the road a bit. So you see, we're using these topics, this set theory, to give us fodder for our writing our proofs. Okay. We got time for one more example. 1.7. A intersect B, the difference of A intersect B and C. So where is A intersect B? This, where A overlaps with B, right? So I'm going to shade. Okay, there's A intersect B. And what do I have to take away? Anything that's in C. So which part's also in C? Right here. So I have to kind of erase. Hope you're not using pen. So let's do this region right here. So this is. That's the Venn diagram for A intersect B minus C. Any questions? Okay. Well, that wraps up all I wanted to really do today. So this was from 1.7. So 1.7 homework. Page 23. Kind of similar to these problems, you're going to be drawing Venn diagrams. So a little known fact, you know who invented Venn diagrams?
Benny Venn.
Venn, I guess it's not so little known, but you know his first name? Anybody read the book? John Venn, of course, you know. I don't know. That's all we're gonna do for chapter 1. We'll start chapter 2 on Wednesday.